We good? I'm
I'm
good.
not touching
You
anything.
did. Well, welcome to the first fresh seminar of the year. Those of you in the room know we've been dealing with some technical issues. We have a new projection system here. Just finally, Janet Newlands helped us get it up and going. So thanks for your patience, both here in the room and elsewhere. For those who are not familiar with our seminar series, we hold these every 2 weeks or so. During the academic year, we'll have a variety of speakers addressing topics of relevance to food and the food industry. It's my pleasure to introduce today's speaker, Abigail Cantor. Abigail is an expert in issues related to water and water distribution, water treatment. She did her undergraduate work in civil engineering at the University of Tennessee and then a master's in chemical engineering at Columbia, and has been here in Madison since 1981, working on a variety of issues related to water, wastewater, treatment and design of facilities to handle water, and more recently moved into issues related to water distribution systems. Of course, that's been in the news quite a bit recently with what happened in Flint and issues going on elsewhere in the country as well. And she's head of a company here in town, Process Research Solutions, which deals with issues related to water safety, water quality, and distribution. So we're very happy to have her here today.
Thank you. It's really nice to be able to talk to groups outside of my own specialty. And you'll see we use the same chemistry and microbiology, and so I think you'll find it interesting as to how it's applied to drinking water quality. And of course, drinking water quality's been in the news a lot this year because at the end of last year became evident that Flint, Michigan had a big water quality issue. And I think it's unfortunate in that it's given everyone the impression that our federal drinking water regulations are ineffective. But that's not true, because when you think about it, we go to any city in this country and we don't think twice about going into a restaurant and drinking the water. And we don't come back with cholera or anything like that. So they have been effective, and they're specifically effective when they address contaminants in source water. So the EPA has toxicologists who tell them that certain contaminants are bad, and there's a certain level that you should not go above, certain concentration. So it's relatively easy to go measure it right where the source water enters the water system. That's relatively straightforward. And then if it's if it's too high, according to toxicologists, then you put a treatment system in. And again, it's right where the source water enters the treatment of the water system. So our problem has come in a lot of confusion about drinking water regulations when it deals with contaminants that are added out in the distribution system. There's interaction between the water and the piping material and just different environments as the distribution system covers the whole geographic area of a city. So the problem is these contaminants change over time and over place. And it creates a lot of dilemmas for us. For instance, where are we now going to measure this contaminant to know what the actual risk to the population is? And how are we going to measure it? We can't go into every home and every building and every tap and find out what the contaminant level is. So we have to do some kind of subset. But when we go into a building, that building has a different piping configuration and water flow and water usage than all the other buildings. So we have a big dilemma of how to measure it. And then what are we going to measure? Because out in the distribution system, there's some reason or reasons that the contaminant is getting into the water, and we have to figure out what that is. So we have to figure out what water quality parameters to measure to express what's going on. And then where are we going to put the treatment system? So the EPA has written various distribution system contaminant regulations, and they try to answer these questions. I find them inadequate to answer the questions myself to my clients. So I developed my own methodology. And it involves a monitoring strategy where I measure quite a number of water quality parameters, more than the regulations say to measure. And I also have my own monitoring station that I developed. And it looks pretty simple. I mean, it is pretty simple, but it's actually an abstraction of a building plumbing system. It gives me data similar to that. And then I have various ways to try to make the data talk to me, so I've had to pull in various data analytical techniques. So this whole program has allowed me to be comprehensive and consistent in every water system that I study. And now I've used the system, I got it pretty much to where it is now in 2006. So I've got 10 years of data of water systems all over this state and all over the country. And it's given me a very interesting view of what's actually going on in water systems and what shapes our water quality. I'm going to focus right now on just the lead and copper rule. First of all, that is a hot topic, and it is related to the Flint, Michigan issue. But let's just compare how the regulation is written and what it predicts is happening versus the actual data that I've gotten from all these water systems that, yes, it's empirical data, but it's very consistently taken and very comprehensive, lots of water quality parameters. So this graph represents the theoretical model that the lead and copper rule is written about. The lead and copper rule is the drinking water regulation, went on the books in 1992, and that's what utilities have to follow to control lead and copper in their water systems. So behind that rule is this theoretical concept of how lead gets into the water from the piping material. And the regulatory view is there's only one way that lead gets into the water. It's through a corrosion process, and the lead comes off of the pipe and forms compounds with carbonates in the water. That's the EPA's view. It's as simple as that. And there's two water quality parameters that control this formation of lead carbonates, and that is alkalinity and pH. Alkalinity is somewhat a measure of carbonate concentration, and then pH. So you can, this representative graph, you can come up, this is the carbonate concentration or alkalinity and pH, and then you can pick off how much your water is going to leach lead out of a lead pipe. One other thing about this graph is that they're saying that high alkalinity water produces high lead, and low alkalinity water produces low lead. So let's take a look at 7 of the water systems that I've studied. I've ordered them by increasing alkalinity, and each one of these systems I ran the monitoring station for over a year in each system. And every 2 weeks I take a water sample from the lead test chamber and have it analyzed for lead. So I've got a trace of lead concentration over time for over a year for each of these systems. So what I did for this next graph is I took an average of the concentration in each of the systems that occurred for over a year. This red square is the average concentration, and then some of the systems had a really big variability of lead concentration, and some had just a very small range within which the lead concentration varied. So that's what these whiskers are coming off of the red squares. shows the variation of the lead concentration over that year. So you can see this is a very large one, this had less variation, so forth. Then what I did was I pulled numbers off of the EPA graph, and this is the predicted lead for these water systems. And basically you can see it doesn't match up to reality. This system number 1, which is the lowest alkalinity water, actually had the highest lead release and the greatest variability. System 7, which is the high alkalinity water, had the lowest lead release and the least variation. So something's missing from their model. And I take so many water quality parameters, I can then do other analyses and look for trends of the lead release with these other parameters, and that's how I come up with hypotheses as to what mechanisms are probably at work creating this high lead concentration. So that's what the 1992 lead and copper rule was based on, and it focused on lead, even though it did have the sampling for copper. But the rule is being rewritten right now. We've been waiting a long time for it to be rewritten, and we've had national arguments long before the Flint, Michigan issue occurred. But it's supposed to be that in 2017, the new rule will be proposed and published by EPA, and then we have a comment period. But there have been groups that have sent in formal recommendations to EPA as to what the new rule should look like, and they are recommending that this actual graph be the basis for how we look at copper corrosion. Once again, the EPA is just depending on alkalinity and pH, and then if you fall into this blue area on the graph, your water is deemed corrosive to copper, and you have to spend a lot of money, do a lot of sampling, and a lot of other kinds of tests, and you can even try to prove that your water is not corrosive. Any water system that falls up here is deemed non-corrosive, and they don't have to do any sampling at all. So let's see how effective that might be. Here's our water systems again that I studied, and once again, here's the data from the copper test chamber, and once again, the EPA predictions of copper release doesn't match reality. The lowest alkalinity system had some of the highest average copper and the greatest variability. And we go to the highest alkalinity system has the lowest copper in this set of water systems and the least variability. And the EPA predicted the copper release to be astronomical. So once again, I can look at a number of factors as to what's going on and come up with hypotheses as to how copper is getting into water in our water systems. And I will say at this point, the number one reason that I see for copper being in the water system is because of microbiologically influenced corrosion. So when I presented these discrepancies at a national conference for the American Waterworks Association, I got a very negative response, and this kind of information is typically sidelined. So I was very fortunate to get a Water Research Foundation grant where I'm formalizing my comparison of the actual lead and copper release in water systems to the regulatory predictions. And I won't go through all these graphs, but there is a PDF of these slides, and you can study them on your own. And I don't know, I just never get it to match up to what the EPA predictions are. So with all these observations in numerous systems, I've been able to try to vocalize what shapes our water quality. And I'd like you to consider this, that when you go to get a drink of water and you turn on the kitchen sink, you fill up your glass. It's not a simple process. That water has gone through a very long journey. And the first thing to think about is that on any water pipe, whether it's out in the water mains, out in the street, or whether it's in your building, there's varying degrees of chemical scales and biofilms on the pipe walls. Now, I probably don't need to define the word biofilm to you guys, but I will briefly say that when microorganisms intend to attach to a surface, they can secrete enzymes that helps them attach, and that material that helps them attach also allows them to pretty much colonize and be safe there. Lots of disinfection can't get through the biofilm, and they can store nutrients and so forth. So that kind of material is interlaced in these chemical scales that are on all pipe walls. Then it's not as simple as H2O flowing through the pipes, hydrogen and oxygen. It's a very complicated solution of various chemicals. Our water comes from natural sources. It's been in contact with rocks and soil and air, and it picks up quite a number of different chemical compounds. In addition, microorganisms are everywhere in nature, and water picks that up, and water has quite a potpourri of microorganisms. Not just the ones that make you sick, the pathogenic ones, but the same potpourri of microorganisms that we're coming in contact with right now. When this very complicated solution of water comes in contact with that very complicated accumulation on the pipe walls, all I can say is very complicated things happen. And here's a diagram to try to give you a sense of all these interactions. There's chemistry going on in the water, and then chemistry going on in the accumulations, and then there's an interaction between the water and the accumulations. Pardon. And the same is true for microbiology happening. And on top of that, there's an interaction between microbiology and chemistry. Microorganisms need chemicals for food, and then they put out waste products, which are chemicals. And the interference of microorganisms into chemical reactions is quite fascinating, but it's very hard to define. I'm trying to say that this is so complicated, what's going on in our pipes, that we can't write a scientific equation to express it. And we can't predict what the final water quality outcome is going to be. So what I'm saying is, EPA, if you're listening, you can't predict the concentration of lead that's going to be in the water, or copper, as an example. So not only do we have this interaction, but we have the results of the interaction. This is what's shaping our water quality, and a lot of bad things can happen. So now I've got a list here of a lot of bad things that we see happen to our water quality in the distribution system. There's lead release, copper release, any number of metals are there, and they are released. There's pathogenic microorganisms that can grow out of control, like E. coli. That will make a population sick. There's Legionella that certainly gets into building plumbing, makes people sick. But there's also the non-pathogenic microorganisms that, according to my observations, cause microbiologically influenced corrosion and elevated metals. Disinfection byproduct formation, which is carcinogenic, and all kinds of things. So what's important to realize is that all of these problems out in the distribution system, they're all interrelated. They're all manifestations of this original problem, and that is the interaction between the complicated water solution and the complicated accumulations on the pipe walls. So let's focus again. Oh, one thing I did want to say is that EPA treats every one of these distribution system water quality issues as separate entities. So there's separate rules for them. And one of the rules is the lead and copper rule, as I mentioned before. And this is their view of what's going on in the water system. They're saying that the water flowing into the pipe only contains carbonate compounds. And on the pipe wall, there's only carbonates of lead and copper. And so based on the solubility of those carbonates of lead and copper is how much lead and copper are released into the final water. So the EPA said, well, all you have to do is adjust the pH and or alkalinity of the water, because that will determine if you can create less soluble carbonates on the pipe wall, and then you'll get less lead and copper release. And if you're not able to do that, you can add orthophosphate. Orthophosphate does combine with lead and with copper and create highly insoluble compounds, and it definitely can lower the lead and copper being released from the pipes. But the problem is we don't have ideal situations like this. We have chemical scales that don't allow this nice barrier to be laid down properly, and we have microorganisms which really throw a wrench into the works, but EPA doesn't consider any of those. With using the comprehensive perspective, what we need to do to solve the lead and copper problem, as well as the other water quality problems in the distribution system, is to physically clean out the chemical scales and biofilms. You'd be surprised to know that many water systems around the country historically put that lowest on the list to flush the pipes and to clean the pipes. So we have some pretty dirty pipes around the United States. And then the other thing is we want to try to control excessive growth of microorganisms. I'm not saying to sterilize the water system. I'm saying let's control the excessive growth of microorganisms, and that has a name, biostability. So what this word means is we're trying to balance the factors that increase the growth of microorganisms against factors that decrease the growth of microorganisms. The goal is to prevent excessive growth, and the goal is to work with all microorganisms, not just pathogenic ones. So what I'm saying is having biologically stable water flowing through clean pipes means you have a very low potential of creating any of these water quality problems that I've talked about. And this is what I see when I go to investigate a water system. Every water system is on a continuum. On one end, the systems that have the cleaner pipes and tanks and the biologically stable water, they just don't have these water quality problems. The other systems, the only thing I could think of when I started seeing these systems and measuring their parameters is they are a soup of metals and microbes. And many of them are not even out of compliance with the drinking water regulations, because the drinking water regulations are not considering a lot of these aspects. And I've seen a number of water systems on this end of on this right-hand end of the continuum. I would say Flint, Michigan has hit the gong there. And I hope that there's not a system worse than that. But I wasn't surprised when it hit the news media, because I have seen these soups of metals and microbes. So I'm not reinventing the wheel here. I'm just taking a lot of data, and taking a lot of data means it leads me into hypotheses of areas of chemistry and microbiology that's already out there in the technical literature. So the problem is our lead and copper rule, as it's written right now and as it's proposed to be in the future, just takes into account this one aspect. And I'm working very hard this year and next to make sure that the lead and copper rule gets moved so that it's representative of the comprehensive perspective. So why isn't it generally accepted? Well, I have pondered this for a number of years, and what I see is that we all have this ideal scientific method in our head where there's a give and take between observations and peer review and so forth, but that doesn't actually happen in reality. There's always politics involved, and there's a certain set of researchers whose word is golden, and they are not measuring for these other parameters. And if they were to measure for these other parameters, they would most likely see that they can't focus on this narrow aspect. So let's talk about Flint, Michigan. You might have heard that if only Flint, Michigan had put in orthophosphate, this wouldn't have happened. I heard that first in every news report that I read. And then in June we had a national conference of the American Waterworks Association. We heard from everybody from people from Michigan who are on a special investigative committee as to what happened, all the way up to the head of EPA drinking water. And they start out by saying, if only they had put in orthophosphate. And I can tell you, I doubt very highly that that's the case. And let's compare it to this comprehensive view and see what makes more sense. I said with the comprehensive perspective, we need clean pipes and biologically stable water. So let's talk about clean pipes in Flint, Michigan. Now this is not a picture of a Flint, Michigan water main. This is a water main in anywhere USA. This is an unlined cast iron water main. They're typically corroded. Those are tubercles of iron particulates, and they're teeming with microorganisms. And I have studied them. I know that when water flows past this, there's a lot of iron particulates entrained in them. When they go into the lead test chamber and the monitoring station, iron has the ability to absorb lead, and so it picks lead up from the surface of the metal plates or the pipes, and I measure very high levels of particulate lead when iron particulates come into a piping system or the monitoring station. This water that passes here can pick up something like 1 million microorganisms per milliliter. And when that kind of water comes into the copper test chamber, I typically measure high copper levels. So all I know in Flint, Michigan, and I have not been working in Flint, Michigan. I've collected my information from news reports and from conferences and technical papers. But Flint, Michigan went broke decades ago, and they have 600 miles of unmaintained water main. So they haven't replaced old pipes, they have not flushed pipes. And I'm just imagining that there's a lot of this in their water distribution system. So I haven't even addressed the lead service lines. On top of having that potential to carry lead throughout the system from the water mains, they also have lead service lines in a number of their homes. And all the lead service line means is there's a large source of lead. And so you've got a big source of lead to transport to the water. But I don't think the news media even realizes that there are water systems around the U.S. that are out of compliance with the lead and copper rule, and they don't have lead pipes. And this is because there's lead in other alloys in the piping system, and certainly in buildings and residences. And they also let off minute quantities of lead. They wouldn't be a problem except for the fact that there's all this these dirty pipes bringing dirty things into contact with them. So Flint has a double whammy of having a very large source of lead in the water system. Then I talked about biostability. and they began to use the Flint river water. Any river water has a high concentration of organic carbon in it, naturally occurring organic carbon, and it has a high population of microorganisms. So, well, of course they have a water filter, so that should take care of it. Well, it should, except that I've taken lots of data around water system filters, and our problem in the drinking water field is that we don't use biostability as a standard of practice. So biostability parameters are not tracked. Nutrients coming in and out of a filter and populations of microorganisms are not routinely studied. What is studied is turbidity. Historically, filters just take out particles from the water, so turbidity is a measure of particles. So I would assume, and I have seen many a filter turn into an incubator where microbiological populations are magnified and organic carbon concentration increases. I'm assuming that occurred in Flint, and on top of that, it turns out that they couldn't even get the turbidity down. The operators were told to start treating the Flint River water. They were practicing offline with their filter. They could not get the turbidity down, and they told their managers, and the managers said, we're switching water sources, so you're open the valve. So we're assuming here that there was a big biological imbalance once they opened that valve. On top of that, residence time in water systems is very important. The longer that water sits around in pipes, the more opportunity that microorganisms have to grow, and residence time is a very big deal in both water mains and buildings. Flint, Michigan has a water system that was built for a population of 200,000, but for decades they've only served less than 100,000. So they have a lot of excess residence time. So yet again, we magnify the microorganism population and nutrients. And then when you take that biologically unstable water and hit what's already existing in the water mains, you destabilize these scales. And that appears to be what happened, because soon after the switch, people noticed discolored water. That's all those iron tubercles breaking up and coming into building plumbing. Then they noticed odors in the water. To me, that says they not only scraped off the top of those accumulations, but they got deep down into the accumulations where everything has gone anaerobic, and that's where a lot of smells come from. Then the water system managers and operators, they have to test for E. coli routinely, and they started getting hits of E. coli out in the distribution system, so they had to order a boiled water order, or put that in place. And then they increased the disinfection concentration to get rid of the bad E. coli. But by doing that, there was now extra chlorine in the system, in a system that had a lot of extra organic carbon. And the combination of chlorine and organic carbon creates carcinogenic disinfection byproducts. Then, of course, we know there was lead release. Of course, people had to plead for their water to be tested to confirm that, and iron release. And then, most dramatically, is a big uptick in people not only getting sick from Legionella, but also dying. And like I said, this fits right into the whole scenario of this comprehensive perspective with all these interrelated problems that occur in the distribution system. And orthophosphate would not have helped at all. In my view, these people have probably been exposed to quite a lot of metals and microorganisms for decades, and it wasn't measured properly. So they couldn't see, the water wasn't discolored, so they don't know that something's wrong. But it's a bigger problem than what just hit I wanna add to the woes here and, make you realize there's additional problems that can occur in buildings. And, I'll just quickly cut to the chase that there's one major problem, and that is modern plumbing design is increasing the residence time in building plumbing. Especially, well, first of all, just so you realize, so you pull water from a water main into a building, and often in a building it's separated into separate piping systems, like the cold water and the hot water could be processed water for an industry or softened water and so forth. And each one of these lines has possibly their own filters and water treatment and storage tanks. So there's lots of complexity to building plumbing. So in residences, there's to me, I haven't proven this statistically, but it seems like an epidemic of water quality issues in new buildings. And whenever I investigate one of these problems, I can trace it back to the plumbing design typically. And the biggest problem in a residence is anytime somebody has a jacuzzi hot tub or a shower tower, they're demanding a lot of water all at the same time, and by plumbing code you have to increase the diameter of the pipes, and then hot water tanks sizes are increased and softeners are increased, so you get this tremendous residence time. And this is also happening to some degree in commercial and industrial buildings. I see oversized softeners and hot water tanks. And that leads to microbiologically influenced corrosion. So the biggest problem I'm seeing, especially in new or renovated buildings, is the corrosion of copper. Sometimes it manifests itself as elevated copper levels and iron and aluminum and other metals in the system. And at other times, the corrosion can actually create pinhole leaks in the copper pipes. It's the property owners responsible for their water quality in their building, but not many people are very aware of all these factors. And I've given a list for commercial, well, residential, commercial, and industrial buildings as some things, maintenance things that you can do to lower the potential for this to happen. So when you get the PDF, if you're interested, you can read through those. And I also, when I realized that there was commonality in these building water quality issues, I put together a little booklet, and it's available for $3 as an ebook on Amazon and other internet sites. But let me just wrap it up here. Just be aware that the focus right now is on the lead and copper rule. It's not because of Flint. It's ironic that Flint occurred when it did. But on a national level, we've been arguing about how to rewrite it since around 2002. And now, by law, they have to get this new rule rewritten, and the proposal may come out in 2017. But I hope you see that the rule is overly simplistic, and it basically causes lots of confusion to not only water utility managers and consumers, but also to regulators themselves. And so I hope if you work with water, whether it's for a food product or for industrial processing in some way, I hope that you also look at these other factors, not just some small subset of chemical factors, but increase those factors and also take the microbiological aspects, the nutrient levels, and the population of microorganisms. There's a really nice new technique as to how you can measure microbiological population. And I hope you do take an interest in this when you hear that the lead and copper rule proposal has come out. I hope you do take time to comment to the EPA on it. Your comments are also valid, whether you're just a consumer or you're an industrial user or it's being used in a product. So, please be aware that this is, going to happen. So if there's any time for questions, I will take them.
Even with all those technical difficulties, we do have time for questions, so fire away.
Very interesting talk. You didn't comment on brass faucets and things, and my understanding is a fair amount of lead in there, and some of that contributes to what you have at least in a household. How would that contribute on an overall basis, do you think, to your way you look at this?
Yes, a lot of older brass has high lead and, also I hear like people have gone and bought fancy Italian faucets and stuff. It has a higher lead level than American brass. Now we have a new rule since about 2 years ago that, low lead brass really means low lead brass. Before, I think low lead brass meant like 5%, less than 5%. So yeah, that's an issue, and that can be a major problem in a home. It follows all these other rules. There's numerous reasons that lead could be coming out of the brass. The first is there is a corrosion process going on. It's like an electrochemical, it's like a battery happening, and there are the processes that EPA says to slow that uniform corrosion down. But there's all these other factors. There's other chemicals like chlorides and sulfates in the water that can can solubilize lead a lot more than carbonates. And then there's the microbiological aspect. So I would say if you have old brass in your home, well, you might consider changing out the faucet to a modern no lead brass faucet or valves and so forth. One problem that I see is we don't consider hot water systems as potable water, so plumbers are putting in high lead brass valves, and it turns out the hot water does communicate with the cold water at the mixing faucets, and a lot of lead or particulate lead especially that I picked up at a cold water faucet actually comes from the hot water system. Other questions?
In the sites that you tested, you found that in a lot of the cases, the ones that had the higher alkalinity actually had less levels of lead and copper in the water. Is your assertion that those systems with higher alkalinity and lower pH have less microbiological activity, and that's resulting in lower lead levels, or is it just
No,
coincidence?
each one of these systems has its own nuances, and there's multiple factors going on at the same time. It just so happened that those 7 water systems laid out like that, but each one, I can tell you a whole story about each one, and there's these multiple factors, and you have to go after those factors from various points and to really take care of the problem. So yeah, no, you can't draw the conclusion like that. It just happened. That very low alkalinity water that I studied happened to be a large water system on the East Coast, and that is a picture of, they've got like 500 miles of water main like that, and that's why they got their big variation of lead and copper. Yes?
So with pictures like this, I anticipate a lot of people stop in the grocery store on the way home to buy bottled water. Do you want to comment on standards for bottled water and how that might compare with some things you're talking about? My understanding is some of the cheap bottled water is just some city's tap water in a bottle, and it's not anything special. What about the standards there?
Well,
Keeping in mind there's 2 bottles of water.
Yeah.
I see that.
Ours is good.
Well, I would not put a lot of confidence in bottled water. The FDA regulates bottled water, and it's a less rigorous testing than municipal water. So municipal water in general, I have more what I, but now I add to that, in any water system that I wanna drink out of, I wanna know how they're cleaning their pipes and if they have biologically stable water. And, those are two important questions to go to your water utility, open public meetings and ask these questions, because, this is the key to America's water quality crisis. The real truth is our water systems have not been maintained. Always at the bottom of a budget is pipe replacement and water flushing, or water main flushing. And then you have to do the water main flushing in a very special way to really get this stuff out. So this is the real issue with America's water systems. And what I would like to see is stop focusing on, oh, just throw orthophosphate, that'll solve all these problems. It doesn't. In fact, it can even make it worse, since phosphorus is a nutrient for microorganisms. But no, the real issue is we need to start replacing our infrastructure, and we have to clean it and maintain it properly. You have to do this very special type of flushing called unidirectional flushing. So, other?
Final questions for Abby?
In your estimation, if they had added orthophosphate into the water at Flint, and sort of taken out the factors of the low pH and the high alkalinity, if it was just microbiological influences alone, do you think the problem would have been just as bad, or be worse, or better?
I don't think it would have made a difference.
Okay.
In fact, it was people from Virginia Tech that came in to actually sample the water after the residents couldn't get any response from their water utility. They took water and they ran offline tests. You can create these pipe loops. And they ran offline tests and put the orthophosphate in, and reported that it didn't make that much of a difference. And that's because the real situation is it was a filthy water system, and they had reached the extremes of an unstable, biologically stable water. And even now, the orthophosphate, now they're back on Detroit water that has the orthophosphate in it, and it's not actually solving the problem. They won't admit that. They say, oh, it needs more time.
All right, well, thank you very much.